if in a circuit we have a constant source voltage V sub S, a capacitance C, which I haven't written in here, but we'll assume the capacitance is C, and a resistance R, then what's going to happen if the capacitor is initially uncharged and we've got a switch somewhere in the circuit and we suddenly close the switch? Well, if we close the switch, we're going to have a flow of charge from positive to negative, meaning that positive charges would be taken off of this plate, negative charges would be moved onto this plate of the capacitor. Now what actually happens, of course, is instead of positive charges being moved onto this plate, it's electrons, which are negative charges, that get moved around here onto this plate, which corresponds to the movement of positive charges away from this plate. Well, let's just say it right now. In a real circuit, the electrons on this plate will be attracted to the positive plate, pumped through the generator, battery, or whatever it is, and onto the negative plate. So this plate will become negative, and this plate will become positive. Now that's what happens when a current I flows in this direction. Of course, that corresponds to positive charges flowing this way. What we've just described corresponds to negative charges flowing this way. The conventional current, recall, is the flow of positive charge, is in the direction of positive charge. Okay, in any case, when the instant we close the switch, there's no voltage across this capacitor. We're going to have the full current, which is just going to be the voltage of the source divided by the resistance. Then charge is going to start building on the capacitor, and as we saw, negative charges will be on this side opposing negative charges, positive charges on this side opposing positive charges. That's going to tend to push the current back this way from positive toward negative, and that's going to resist this flow of electrons. And what we get then is at any instant the current is going to be the total voltage, which is going to be the source voltage, which goes this way, minus the capacitor voltage, which is pushing in this direction, divided by the resistance. That current is exactly what deposits charge or takes charge away from the different plates of the capacitor. So this current is the rate at which the charge in the capacitor changes. Now, the thing we're trying to understand here is, why does the source get easier and easier to crank if we're cranking the generator? Or if we have a battery, why does the source make less and less demand on the energy stored in the battery? Or why does the circuit make less and less energy demand on the energy stored in the battery as the charge builds on the capacitor? Okay, now let's go back to thinking we're cranking, and we know that as we crank, it gets easier and easier to crank. Why is that? Well, that's because less and less current is flowing. Less and less current is flowing because as we crank, we charge up the capacitor, which fights the voltage, or fights the tendency of the generator voltage to pump electrons through the surface. Now you might think if we have a voltage here that's fighting our voltage here, that would cause more work. But what the voltage is doing, what the voltage here and the voltage here are doing, is they're trying to push electrons through the circuit. If they're not successful in pushing them, if the source is not successful in pushing a lot of electrons through the circuit, then we're not going to get much resistance, or we're going to find it easier to crank. There'll be actually the resistance of the circuit stays the same, so we don't want to think resistance when we're thinking of how hard it is to crank, as we've seen. But the idea is that as the capacitor charges up, we get less and less flow of electrons, so that despite the fact that we're creating the same voltage here, we're having less and less success pumping electrons through, and as a result we get easier cranking. And recall, that's because the electrons, as they go through the circuit, dissipate energy. And if we don't move charges through the circuit and through the resistance, we don't dissipate energy, we don't need as much force to crank. When the capacitor gets fully charged, we have a voltage across the capacitor, positive here, negative here, which fights the voltage across the source, positive here, negative here. The positive here wants to push this way, positive here wants to push this way. We get zero current, which means that it doesn't take us any effort to crank the generator. There's no demand placed on the battery. Now actually with the generator we do get a little bit of effort. We do have to exert a little bit of effort because of the friction in the bearings. If this is a battery, there's very, very little demand made on the battery. Actually no demand made on the battery. Nothing's flowing. We're not dissipating any of the chemical energy charged in the battery. Okay? The other part of this is that there's no voltage across the resistor. Over here, the voltage across the resistor is, as we saw, the difference between the voltage of the source, which is pushing this way, and the voltage of the capacitor, which is pushing this way. If we move around the circuit, the voltage drops. And the voltage drop has to equal the voltage drop of the source, or the voltage gain of the source, in this case. Okay? So as we go around the circuit, we got a voltage drop across here and a voltage drop across here. When we get to this situation where the capacitor is fully charged, the voltage across the capacitor equals the voltage of the source, and as we go around the circuit, the whole voltage drop occurs across the capacitor, and then the voltage raises across the source again. And there need be no voltage drop across the resistance, meaning no current. Okay, in this case, the only potential difference is across the source and across the capacitor. Now, if we disconnect the capacitor and then connect a voltmeter in parallel with the capacitor will discharge through the voltmeter. Let's say that right now. The capacitor will send a current through the voltmeter. The capacitor will discharge through the resistor, but it'll send a current through the voltmeter. Now it sends a very small current through the voltmeter because we have a large resistance. Rm, the resistance of the meter, is very large compared to this R here, which means that as the current flows, very little flow is going to occur across the meter. Now, the meter consists of a galvanometer in parallel with a large resistor. So we have a tiny current. Im, the current through the resistor, is very small. In the case that we look at in class, it's on the order of 1,000th the current through here. That's assuming that we have a resistance of about the resistance of the generator on the order of 20 ohms or something like that. And the resistance that we measure in the meter turns out to be around 50,000 ohms, so it's even less than 1,000th the resistance here that we have here, so that the current here will be less than 1,000th of the current that we have here. In this case, the capacitor discharges through this resistor. The time that we observe to go from 10 volts to 3.7 volts was 2.6 seconds. Now if we go back to the expression for the voltage on a resistor, in this case when we have a capacitor discharging through a resistor, we have the e to the negative t over RC. We go from 10 volts to 3.7 volts because from 10 to 3.7 is a factor of 1 over e, meaning that as we go from here to here, the time t goes through one time constant. We saw that earlier, and we're just using that result. The result here then is that the resistance is 2.6 seconds over the capacitance. Okay? If we measure the time to go from some voltage to 1 over e times that voltage, then RC, the time constant, is going to equal that time, and R is going to be that time over C. And if we solve that for the 0.47 farad capacitor, we see that we have a 5 ohm resistance. And this would be the estimate of the resistance for the situation.